Okay, so I'm starting the class. So yeah, so till now we have learned about Newton's laws of motion, force, friction, momentum. But the biggest problem student face is which force is acting and where. How we can find out which force is acting and where. So to solve this confusion, we use a very powerful tool called free body diagram. So today we are going to study about first topic. Our first topic is free body diagram. We also called it as FBD. So what is a free body diagram? A free body diagram is a diagram that shows all the forces acting on a body. I'm writing it. There is something of a free body diagram is a diagram. I guess there is something. Let me check if there is something going on. Um, just give me a minute. Okay, I'm writing it again. There was some issue there. Okay, today we are going to study about free body diagram. Uh, I think I should start recording here as well. Can I do this? In last class, we lost the recording, so I think I should record on two places so that it can't get lost. Okay, so the definition of free body diagram is a free body diagram is a diagram that shows all the forces acting on a body. Is a diagram that shows all the forces acting on a body. So in FBD, we do not draw surroundings. We draw only objects. Like we draw only the objects that we care about, that we want to, that what force are acting on that object, and we show all the forces acting on it. In if you draw FBD correctly, it will solve half of the numerical problems already. Okay, so why is FBD important? Without FBD, student apply wrong forces, direction mistaken happen, equations become wrong. So to solve all these issues, we use free body so that the forces become clear to you, the direction are correct, Newton's law can be applied easily. So there is a rule that you should never solve a mechanics problem without drawing FBD. So there are some steps to draw FBD. Steps to draw FBD. You should always follow these steps. Step 1 is draw the object clearly. Step 2 is isolate the body. Draw the object that you care about, that you want to know about, only that body. Isolate the body from everything, every surrounding. Show all the external forces. So why we write external forces? Because we don't care about internal forces. There are several internal forces acting in an object. Like if there is an object, in this there is atoms and they exert force on another exert force on them. There is many forces going on in the many random forces going on, and all the forces sum up to zero. They doesn't affect the outer world. So we don't count the internal forces. We always count the external forces that are going that are coming from outside. That's why we write external forces. After showing all the external forces, we have to apply the second law of motion. Newton's second law, which is summation of force is equals to mass into acceleration. And what we do, we do in both direction. We do in x direction, then we do in y direction. Sum all the forces and then write F is equals to summation of all forces is equals to mass into acceleration. There are some common forces that will apply, or that will apply on every kind of body, that you should never miss. So there are some common forces. I am writing those common forces for FPD. So first is weight, that is mg. And we know the gravitational force on every object is always applying. We have to always apply gravitational force on the object, unless question says that it is a gravitational force free environment. Unless it is given, we should apply all the forces. Second is normal force. In normal force are perpendicular to the surface. Let's say this is ground and here is an object placed on the ground. The normal force are always perpendicular to the surface. It is like this. Normal surface always like this. Third is friction. If question says that it is frictionless, then we don't include friction. If question says it is friction, it is a rough surface, we always apply friction. And friction always apply in opposite to the motion or tendency of motion. Let's say if this object is moving this in this direction, or if any force is applying in this direction, let's say, and it is about to move in this direction, then friction will apply in opposite to the motion.
Ma'am,
Yeah.
ma'am, can you share your screen?
Oh, sorry. Oh, mm, just a minute. Mm, Photos. Can you see my screen?
Yes, ma'am.
Okay. So are you there all through this? I am just repeating in short, okay? So that you understand. Okay?
Yes, ma'am.
So today we have started the topic free body diagram. In this, the free body diagram is a diagram that shows all the forces acting on a body. Like if we have to what to do, there are steps to draw free body diagram. First of all, we have to draw the object very clearly, and second is we have to isolate the body, whichever body we are talking about. We have to isolate the body so that we can see clearly what are the forces is applying on this body. And then we have to show all the external forces. We should not include any kind of internal forces. We have to show all the external forces, and then we will apply Newton's second law of motion. And what we have to do is we have to do apply Newton's second law in x direction and also in y direction, so that we can see what is happening in x direction and what is happening in y direction. There are some common forces in FBD that we should remember, and we should always apply these forces. First is weight. As we know, weight always apply on the body, that is gravitational force always apply on the body in the downward direction, which is mg. Second is normal force. Normal force will be perpendicular to the surface. So our surface is this. So normal force will be perpendicular to the surface. So normal is will be shown like this. Third is friction. Friction always applies in opposite to the motion or tendency of the motion. Let's say if our body is moving in this direction, our friction will be in opposite direction. So this is a friction. Now fourth one is tension. T, it will act along the string. Let's say if there is another object and both are attached to a string, there will be tension in the string, and this string will pull this object in this direction with T tension, and this object in this direction with T tension. So this is the tension. Wherever there is a string, you should always mark the tension. And fifth is applied force. Any force that question says that there is this force that is applying, we will show that force. Let's say I am saying this force is applying on this object. So we will show that force. And then we write the second law of motion, that is F is equals to ma. Let's say I say this block as A. So now what we do, we isolate the block A. First, mention the weight. Weight will be, let's say its mass is m, then weight will be mg. Second is there is contact surface, so there will be normal. So normal force is acting upward direction n. I am saying that there is a force acting this side on it. And third is it is attached to this string, so tension is there in the left direction, so there is this tension. Fourth is Fifth is the friction. This is rough surface, so there is a friction force opposite to the direction of motion. Now how we can apply, tell me when I pull this object, let me change the color, this object by this force, where will the object move? In which direction? Can you tell me?
On right side.
Yeah, right side. Will it move upward or downward?
No, ma'am. Right side.
Yeah, right side. Okay. So we know that it will not move upward or downward. Like in y direction, in this direction, this upward downward direction, there is no movement. That means there is a net force 0. That's why there is no movement. So what we will write, the uh, second law says we have to write summation of all forces is equals to mass into acceleration. Now I am writing the forces of y direction. This is n and it is upwards. So I am taking upward positive and downward negative. So first I will write upward force, that is n normal. Second force that is acting in y direction is mg downwards. Because it is downwards, I am writing it minus mg. And since there is no movement in y direction, so it means the acceleration of this object is 0. So I'm writing acceleration is equals to 0. So I will get n minus mg is equals to 0. N is equals to mg. From here we get that this normal force is equals to this mg force from my y direction. Now I am writing the second law of motion for x direction. Summation of F is equals to m into a. Summation of F. First, there is this force acting in right side. I am taking right side as positive and left side as negative. So we will write F. Now the other x direction force is T and it is in left direction. So we will write minus T. Other force is friction, which is in left direction. We will write minus F is equals to mass. And since it is moving forward, so there will be some acceleration that I am writing A. From here, we can get acceleration value. Acceleration is equals to, we do cross multiplication and we can write F minus T minus small f, that is friction, upon m. This is the acceleration of this object. Do you understand?
Yes, ma'am.
So like this, we will solve all the problems, all the numericals, and it will be easy. Once you draw the FBD diagram, it will become very easy. You can see all the things very clearly. So tell me, if there is a block, another example, if there is a block which is moving in this direction with velocity v, with constant velocity v, what will be the net force on this object? What is the net force on this object? Can you tell me?
Ma'am, 0.
Yeah, right, 0. Since it is moving with constant velocity, it is 0, because if there is any force, then there will be acceleration, and if there is acceleration, there is change in velocity. So right, you are right. Net force is 0. In this case, net force is 0. Now I'm going forward. Let's solve some question. Okay, in this first part, I let's say this body is A and this is, let's change the color. This is B and this is A. The acceleration that I have found is acceleration of A. As you can see, I have drawn the object A. There is object B. I haven't drawn the FBD of object B, and neither I have found out the acceleration of object B. Can you find out the acceleration of object B?
Yes, ma'am.
Yeah, solve it. Let's suppose there is no friction here where object B is placed, there is no friction. Object B mass is MB. Salt?
Ma'am, the only force acting on object B is tension, ma'am.
Yeah,
Then acceleration is equal to T by M, MB.
yeah, right. The free body diagram of object B will be there is tension T and there is mbg gravitational force and there is normal in upward direction. Since there will be some acceleration of b, we can write for x direction summation of f is equals to mab. Summation of f, there is only in x direction there is only one force, that is t. We can write t is equals to mb ab. So ab will be t upon mb. This is acceleration. And second equation we can write in y direction is summation of f is equals to ma. In y direction there is normal upwards minus mbg, and since there is no acceleration in y direction we can write it as 0. So normal is equals to mbg. Yeah. So now we are going towards our next topic, that is inertial and non-inertial frames. Inertial and non-inertial frames. There are two types of frames. In one is inertial, another is non-inertial. This is slightly different topic that from all the topic that we have studied till now. This is this topic comes from the concept of frames of reference. That from where we are observing, from where we are seeing our object. To describe motion, we need an observer, a reference frame. To describe any motion, we need two things. First is an observer, and second is a reference point or a reference frame. So, uh, let's say there is an object on the platform, on the train platform. Okay. And one person is sitting in the train, and one person is standing on the platform. And there is an object just placed on the platform. Train is moving. The person that is on the platform, the object for, let's say this is platform and this is train and it is moving forward, and this object is placed here and someone is standing here and one person is inside the train. For this person, this object is not moving. This object is where it is placed. But for this person, it feels like the object is going behind. Have you observed this? When you are sitting in a train, you feels like the other things on the platform is going behind. Have you observed this?
Yes, ma'am.
Right. This is called the frame of reference. This observer on the platform is seeing the object as rest, and the observer in the train is seeing it as it is in motion. So there is a change. There is change of the concept when we see it from a moving object or from a rest object. That's why it is very important that we know the concept of reference frame, that where we are observing the object. And from here we come to this topic, inertial and non-inertial frame. So inertial frame, the condition for the inertial frame, when we called a frame is inertial. So a frame of reference is called inertial if so the a frame of reference is called inertial if there is two condition. Any one of them is true, then the frame is called inertial. If a body is at rest, then we call this frame as inertial. Or if it moves with a constant velocity, then also we call it as inertial. Now in this case, there is this boy that is moving in the train. It is, let's say it is an accelerated train, and the boy on that is standing on the platform. Tell me which is inertial, in the train boy or in on the platform boy?
And on the platform.
Right, because yeah, he is at rest, so we call it as uh, inertial frame. All the Newton's law of motion is valid in the inertial frame. In an inertial frame, Newton's laws are valid. There is nothing worried about inertial frame. All things goes as we studied earlier in the inertial frame. There is no change. Like person standing on that platform, or even if this if this train is moving with constant velocity, then we consider this as inertial. But if it is moving with some acceleration, then we can't consider it as inertial. Now we will talk about non-inertial frame reference. So non-inertial frame reference में a frame of reference is called non-inertial if it is accelerating. There is only one condition. A frame of reference is called non-inertial if it is accelerating. Like in this case, if the train is accelerating, the train frame is non-inertial. In non-inertial frame, we cannot apply directly the Newton's first law. The Newton's first law fails in non-inertial frame. We Newton's first law fails in non-inertial frame. So what happens in non-inertial frame is we feel extra forces. We feel extra forces in this. As you can see here, actually, this object is at rest. The person on the platform sees the object as rest, but the person in the train sees it like it is going behind. And since this person is sees like it is moving, so he might think that there is some force. If we see motion, there will be some force. That's why there is motion, accelerated motion. So the reason behind it is we feel that it is there is some force that is acting on that object. So we feel that extra force. In reality, there is no force, but we feel it. So this force that we are feeling, since it is not real, so what we called it for the concept and to study it, we called it as pseudo force. This extra force that we are feeling, we called it as pseudo force. From this name itself, it says that it is not real force, but to solve the question and to understand things, we use pseudo force. There is the force that we are feeling. So this is the new concept that we have to study in the non-inertial frame. In inertial frame, there's everything is fine, nothing will change. But if we are observing an object from any moving accelerated motion, then we can't solve it directly from the laws of motion. We have to apply this pseudo force, then we will solve the question. So to apply Newton's laws in a non inertial frame, we introduce a pseudo force. So pseudo force, there is some condition for pseudo force. First is condition. First is it always acts opposite to acceleration of frame. It means that from where we are observing the object, the acceleration, the motion of the frame where we are standing, the force on that object will act in the opposite direction, and its value must be ma. This acceleration of that object, of that reference frame, and mass of the object. Let's say in this case, the example of train and boy, the train is moving in this direction. Let me change the color. The train is moving in this direction with acceleration a, and what he's seeing, this object is going behind. Since this object is going behind, there must be some net force behind, so that this object is going behind. So that is what the pseudo force comes in, and we apply the pseudo force as ma, the acceleration of this train into mass in opposite direction. You can see that train is moving in, let's say, in downward direction, or say south direction. We can't say downward. Let's say it is going in the south direction, but the object is going in the north direction. So we always apply the pseudo force in the opposite to the acceleration of frame. Um, if you ever do you feel that if you are sitting in a car and there is a sudden turn appears, and when a car take that turn, you felt a force outwards.
Yes.
That force is the pseudo force, because for the in inside the car, it feels like you are at rest, but for the outside it feels like you are moving. And that force, that pseudo force, we call it the centrifugal force. In so in a rotating system, it is called rotation. As you can see that you take a turn, you are rotating. In rotating system, that pseudo force, we have a name for that pseudo force, and it is called as centrifugal force. Like if this is a car and you are taking this kind of turn, so the person inside the car feels some force exerting outwards. This force is centrifugal force. Um, so the topic ends here. Whole laws of motion topic completed here. Now tell me, till here, you have any doubt? Do you have any doubt?
No, ma'am.
Everything is fine?
Yes, ma'am.
Okay, so now I'm taking some questions. So first question is, which of the following will always be in the direction of net external force acting on the body? First is displacement. Second option is velocity. Third option is acceleration. Fourth is change in momentum. Tell me, which is the right answer?
Ma'am, can you explain the question again?
Sorry, can you say again?
Ma'am, can you explain me the question?
Question is, which of the following will always be in the same direction of net force, net external force acting on the body? It means the direction of displacement, that the direction of net force, let's say an object and its net force direction is this. So it is asking that the direction of that net force, in which, for which of the following option the direction will be same. The direction of displacement and this net force direction will be same, or the direction of velocity and this net force direction will be same, or the direction of acceleration and this force will be same, or the change in momentum and net force direction will be same. Tell me in which case the direction of net force and direction of which of the following option will be same.
Acceleration.
Right, for acceleration. Where the force direction, net force direction is, the acceleration of direction will be same as the force direction. Can you give me an example of where the displacement direction is different from the force direction? No?
No, ma'am.
Okay, when you throw a ball in the air, let's say you throw a ball in the air. When the ball is in the air, what are the forces acting on the ball?
Ma'am, gravity.
Gravity. Any other?
Mm, Some
No?
external supply, ma'am.
What? Say it.
Ma'am, ma'am, we throw it is with the force, ma'am. That force external force, no?
When at the initial moment when we throw it, we give it some force, but when we leave it in the air, there is no contact between our hand and ball, right? So when it is in the air, there is no force from me, right? So there is only one force, gravity, acting on it. And for the if only one force on the body, so direction of the net force is mg. So direction of force is downwards, net force. But body is moving upwards. So you can see this example, the displacement and force have opposite direction. Similarly, the velocity is also upwards. So direction of velocity and force is in opposite direction. But for acceleration, it is always in the direction of net force. Right? Now we go forward with the next question. When a constant net external force acts on an object, which of the following may not change? First is position, second is speed, third is velocity, D is acceleration.
And
Tell me.
velocity.
No, wrong. So, what question is asking, when a constant net external force acts on an object, which of the following may not change? That there is external force, but which of the following will not change? So, position. If there is some force acting on the object, position will change. Definitely, position will going to change. Speed. Speed is something that not change. Force in force. Okay, I'll take the example of circular motion. If anything is going in circle, one force is always acting towards the center, right? So force is acting towards center, and there is some speed to this object. There is velocity have magnitude and direction. Magnitude and direction, but speed have only magnitude. So if it is moving, let's say, with 4 meter per second, constantly with 4 meter per second, and it is only changing the direction, and since it is changing the direction, this is because of this force, but it is not changing its speed, that is its magnitude. So its speed might not get change. So one is this, and second is velocity will definitely change. Either in terms of direction, there is no change in speed, but there is change in direction. So velocity will change. There is no change in acceleration. When we write F is equals to ma, we say that a is constant. We cannot say a is variable, that a is changing. We are saying that a is constant. So acceleration will not change. So B and D. Do you understand this concept?
Yes, ma'am.
Okay. So now there is question, in which case will there be larger change in momentum of a 2 kg object? First is when 10 Newton force acts on it for 1 second. Second is when 10 Newton force acts on it for 1 minute. Tell me, in which case there is a larger change in momentum?
Then option B.
Yeah, right. We can see that in 1 second there will be some acceleration that increase for only 1 second. In larger time there will be change in the velocity very large. So mass is constant and what is momentum? Mass into velocity. So in second case there will be larger change, right? Okay, next question is a ball of mass 0.2 kg falls through air with acceleration of 6 meter per second square. Calculate the air drag on the ball. Solve it. Do you understand the question?
Yes, ma'am.
You are solving, right?
Yes, ma'am.
Okay.
Then force is equal to mass into acceleration, ma'am.
Right.
Then force is equal to 1.2 Newton, ma'am.
The air drag on the ball, you are saying
2, ma'am. 1.2 Newton.
1.2 Newton. Okay, I'm solving it. Then you see and tell me that you solved it right or wrong. Okay. So what we do, first of all, we draw the free body diagram. As I have said, when we draw free body diagram, it is very easy to solve the question. So when we throw a ball, it is not like only mg is applying in real life. Theoretically, we assume that only gravitational force is applying, but there is air and there is a resistance of air, the drag of air. If you uh, let's say drop a paper, have you seen the paper floating in the air? It will not directly comes to ground. It floats in the air. It means that there is some force from the air that is applying on it. So what we do, and in the question it says that there is air drag. So first of all, there is mg applying on this. So the mass of let's say write mg here, and the air drag. If we drop the ball, the air drag will be upwards. Let's say I name it as air drag as f. And in the question, it is given that there is an acceleration downwards. It is 6 meter per second square. So in x direction, there is no motion. So I am not considering any x direction thing because in x direction, there is no force. So this is not my concern. I will go in y direction. So I'll write summation of all the forces is equals to mass into acceleration. So F, the force, the air drag that I've assumed is F, and mg is downwards, so minus mg m and acceleration is given as 6. I'm not writing the unit here. We will write unit later. So we have to find F. We write F as it is. M, mass is 0.2 kg. And G, we will normally take G as 10 meter per second square. If the question given or question calculation ask us, then we take is 9.8 meter per second square. So I'm taking it as 10 here. Mass is 0.2 into 6. So F minus 0.2 into 10 is 2 is equals to 6 into 0.2 is 1.2. So F is equals to, we will take 2 on the right side, 2 plus 1.2. So F is 2.2 Newton. Do you understand? Oh, sorry. There is mistake done by me. Let's erase all this. Okay, so there is this thing given us that acceleration is in downward direction, right? So what we will do wherever we have this thing that motion is in this direction, so we can take our positive direction and negative direction as we want. We can take one direction as positive and the other direction automatically becomes negative. It will only give us the direction, but we have to make sure the all the same direction thing, like mg and 6 are in the same direction, so the sign for both of these will be same. What I have earlier did, I forgot about the sign and I've solved it, then again I have realized that I have done wrong. So what I have to do is, we to simplify the calculation, we always take positive in the motion direction and the opposite will be negative. So in this case, the motion is downwards. So what I am taking is the in downward I am taking as positive. So I will write mg. At the moment when I take downward as positive, the upward becomes negative. So minus f is equals to m into a. Then we will put the value. 0.2 is mass and 10 is g. 0.2 into 6. Now 0.2 into 10 is 2 minus f is equals to 6 into 0.2 is 1.2. So now I will take 1.2 on the left side and f on the right side. 2 minus 1.2 is equals to f. So 2 minus 1.2 is 0.8 is equals to f. So now you can write it as f is equals to 0.8 Newton. So this is our answer. The drag of the air on the ball is 0.8 Newton. Do you understand this concept?
Mm.
Is there any doubt? If you have any doubt, you can ask.
Mm.
Okay, so this chapter ends here, and now we will begin next class with another chapter. If you have any doubt anytime, you can ask. You can put your questions on classroom as well in the comment section. Any comment you can ask, I will answer that there. And if you have some question, you can ask in class. And apart from class, you can ask in classroom. Okay, try to read and solve as many questions as you can so that you will do good. Okay,
Mm.
is there any doubt, anything?
Mm.
Okay, so I'm winding up the class.
Thank you.
Thank you.